Okay, hello and welcome everybody to the worked example section for linear maps and inverse linear maps. I'm going to start off today by noting something that you probably glossed over in calculus. It's actually a much more important fact than you realize at the time, and that is the fact that the derivative d dx, which maps, let's say, a vector space of functions, so we'll call it v, but v will be the space of functions, maybe from R to R, which have any number of derivatives to itself. So the derivative as a map, that's really what's going on here, is I'm considering the derivative as a map on a vector space, is a linear map on these vector spaces. And in calculus, it would have been referred to as, the derivative is linear. That's how they would have said it probably. But I don't think any of you would have paid much attention to that language to call it linear. You would have paid attention to this property. Everybody pays attention. If you do a f of x plus b g of x, this equals a times f prime of x plus b times g prime of x. This is everybody's favorite property of derivatives, distributing over addition and commuting with scalar multiplication. This is linearity. This is a linear combination. So the derivative of linear combination is a linear combination of derivatives. And so you have this property that the derivative is a linear map, and I don't think too many people stress that, but it is incredibly important because it means that our life dealing with differential equations can be made easier by applying properties of linear maps and their inverses. By the way, I don't think it's too hard to believe that the inverse of a derivative is the integral, the antiderivative. And that's only true for on spaces without constants. That's kind of the reason why you need the plus c sitting around. But either way, there is an inverse linear map to a derivative, and that is the integral. So that's just something really nice to keep in mind. Also keep in mind the study of differential equations, linear differential equations, is the study of inverse linear maps on function spaces. So just something good to keep in mind as we continue. This is incredibly relevant, not only just as linear maps, because we do live in a three-dimensional world where linear maps within 3 dimensions exist, but we also exist in a world where differential equations are very important. So thinking about linear maps as derivatives or as just these finite dimensional objects that we encountered earlier is both useful. Both perspectives are very useful. Let's go back to kind of today's working exercises, which we're going to start with is the map L of x1, x2, which equals 3x1 minus 2x2, x2, and x1 plus 2x2 linear. And this is a nice example of a map where the domain is two-dimensional, either C2 or R2, doesn't really matter, and the codomain is C3 or R3. It's a three-dimensional codomain. So this is a nice example of a linear map where the input and the output are not the same vector space. They have different vector spaces. To the input versus output. So it's good to just keep in mind that linear maps don't have to map the same space to itself. They can definitely trade spaces, which is kind of good. Just gives us the ability to work with a wider range of objects. Let's test if it's linear. So if you remember from the last video, what we need to do is compute L of a linear combination of vectors. So I'll say AX plus BY. and simplify. Well, how could we do this here? In the inputs, right? These are the inputs, are two-dimensional. So we could write ax as ax1, x2, and by as by1, y2. Or I could write this as ax1 plus by1, ax2 plus by2. So that can be my input. And I'm thinking here that that is a placeholder for these two objects, and that is a placeholder for these three objects. So it's not actually x1 and x2s that are in there, but rather placeholders. And so I can compute L of ax1 plus by1, ax2 plus by2 as, using my placeholders, 3 times the first entry, which is ax1 plus by1, minus 2 times the second entry, which is ax2 plus by2. And then in the second row, I just have the second entry, which is ax2 plus by2. And in the third row, I have the first entry, ax1 plus by1, plus 2 times the second entry, which is ax2 plus by2. If I want to simplify this, every time I simplify, really I should be thinking about simplify as in factor out a's and b's. That's what we want to think and simplify. So we're going to combine every term with which has an a in it. We've got 3ax1 and negative 2ax2, which will be a 3x1 minus 2x2, plus combining all the terms with b in them. I have 3by1 and negative 2by2, so I have 3y1 minus 2y2. Everything's already written in terms of a's and b's in the second row, which is useful. And then in the third row, if I'm combining my a's, I have ax1 and 2ax2, or a times x1 plus 2x2, plus all my terms with b's in them are by1 and 2by2. So I've got y1 plus 2y2. That's me computing and simplifying. In step 2, I'm going to compute the associated linear combination, which is a L on the vector x plus b L on the vector y, which here will be a L on the vector x1, x2, plus b L on the vector y1, y2. That's going to look like a L on the vector x1, x2. So the first entry goes into 2 different places, and the second entry goes into 3 different places. I'm going to go ahead and write this now as 3x1 minus 2x2, x2, and x1 plus 2x2. That's the inputs x. The inputs for y are going to be 3y1 minus 2y2, y2, and y1 plus 2y2. And then I also simplify. And simplify, which in this case means combining into a single vector. So now that I have this, I'm going to go ahead and combine this into a single vector. And to combine into a single vector, I'm just going to distribute the a's across, the b's across, and utilize the plus. This is going to give me a times 3x1 minus 2x2, plus b times 3y1 minus 2y2. It's going to give me a times x2 plus b times y2, and finally it's going to give me a times x1 plus 2x2 plus b times y1 plus 2y2. In step 3, I compare 1 and 2. And I notice in this case, how do 1 and 2 compare? We're looking here and here. And you'll notice they are the exact same. They are the same. So L is linear. That's a nice example of a linear map between 2 different vector spaces. Let's test one more question in terms of checking or verifying if something is linear. So I'll ask the question, is L, which maps x1, x2, x3 into x2 plus 1, x3 minus 2x2, and x1 squared. I'm going to check if this is linear. So what we're going to do is follow the same steps as before and compute L of ax plus by. The inputs are 3-dimensional today, So we're going to have, and I'm skipping a few steps because I think you're all getting used to this, ax1 plus by1, ax2 plus by2, ax3 plus by3. Now we ask ourselves the question, what does this evaluate to? Well, I'm looking at my first output, which is x2 plus 1. I'm going to grab the second entry, and I'm going to add 1 to it. It's going to be ax2 plus by2 plus 1. I'm going to grab the third entry, minus 2 times the second entry. So the third entry, minus 2 times the second entry. ax3 plus by3 minus 2 times the second entry, which is ax2 plus by2. And finally, in the third component, x1 squared, I'm going to grab the first entry and square it. First entry is ax1 plus by1, and I'm going to square it. Now I need to simplify. And here I can simplify, can't really simplify the first entry too much, that's just ax2 plus by2 plus 1. The second one I can combine terms with the a's in them and the terms with the b's in them to give me ax3 minus 2x2 plus by3 minus 2y2. And in the third entry, I can FOIL that out to give me a squared x1 squared plus 2ab x1 y1 plus b squared y1 squared. That's about as simplified as it gets. Second, let's compute the linear combination of L on each of the vectors. It's going to be A on L of the vector x1, x2, x3, plus B on L of the vector y1, y2, y3. And we're going to be left with, if I calculate each of these out, what is L of x1, x2, x3? This is just the L given to me up top. x2 plus 1, x3 minus 2x2, and x1 squared. L of the y's, I'm just going to replace each x with a y. That's y2 plus 1, x3 minus 2x2, and y. I said I would replace each x with a y, but I didn't. y3 minus 2y2 and y1 squared. And then if I go ahead and multiply each of my terms by an a, each of my terms by a b, and add the terms together, I end up with a x2 plus a plus b y2 plus b, ax3 minus 2ax2 plus by3 minus 2by2, and finally ax1 squared plus by1 squared. In step 3, I'm going to compare 1 and 2. And in this case, when I compare the two of them, let's just even compare the first row. I've got an ax2 and a by2 there in the first row, but I have a 1 over here and I have an a plus b over here. So already in the first row, they are different. That's good enough to say different, hence nonlinear. However, I could look at my second row, and in fact they are the same on the second row, but even if I look at the third row, a squared and a, b squared and b, and 2ab, and there's really no 2ab even in the third row. So actually both the first and the third row is different too. So only the second rows agree, and if any of them disagree, then we are nonlinear. Now we end up caring because the Schrodinger equation, when I write down that h hat in the Schrodinger equation, that will need to be linear. And so that's why we do care about making sure that these are the case. It turns out that if you're trying to develop a physical system that you want to work quantum mechanically, you can verify your model by first checking if it's linear. This isn't always the case, but this is the case certainly in an introduction to quantum mechanics situation. Let's look at some examples of inverses. And maybe even only one example. Let's find the inverse map for L of x1, x2, x3 equals 3x1 minus x2, x3 minus x2, and x1 plus x2 plus x3. So we're going to find the inverse linear map here. And let's recall how we do this. We just write L of y equals x and solve for y. but really that means in this case solve for y1, y2, y3. So L of y1, y2, y3 equals x1, x2, and x3. That's going to give me the output, but in y's, 3y1 minus y2, y3 minus y2, and y1 plus y2 plus y3 is equal to x1, x2, x3. Now keep in mind the solve for y is technically step 2. We're going to go ahead and write this as a system of equations by reading off horizontally 3 equations. Those equations are written as 3y1 minus y2 equals x1, y3 minus y2 equals x2, and finally y1 plus y2 plus y3 equals x3. I still like the substitution method best, so I'm going to solve for y2, which is going to give me that y2, I'm bringing y to the right and x1 to the left, is 3y1 minus x1. And now that I know that, I can grab that version of y2 and plug it in the 2 other cases when y2 shows up. That's going to give me y3 minus 3y1 plus x1, because I've distributed the minus sign, equals x2, and it's going to give me y1 plus 3y1 minus x1 plus y3 equals x3. I can play the same game as before and go ahead and solve my second equation for y3. And if I solve the second equation for y3, I end up with y3 is equal to 3y1 minus x1 plus x2. And now that I've solved for y3, I can use it and plug it in for y3 in my third equation. The third equation will then become y1 plus 3y1 minus x1, and now y3 is 3y1 minus x1 plus x2, and this is all equal to x3. You'll notice now there's only one term with a y in it, and they're all y1s. So I have 7 total copies of y1, and if I bring every term with x to the right, I have 2 copies of x1, I have a negative x2, and a positive x3. I could divide by 7 and recover that y1 is 2/7 x1 minus 1/7 x2 plus 1/7 x3. Having found y1, I can plug it in to the equation for y3 and recover that y3 is equal to 3 copies of y1, so I'll just distribute a 3 across and get 6/7 x1 minus 3/7 x2 plus 3/7 x3, and finish off the equation with a minus x1 plus x2. I can then combine all terms of x1 and x2 and subtract off 7/7 and end up with negative 1/7 x1, add 7/7 worth of x2 to recover 4/7 of x2 and 3/7 of x3. So this is now going to be y3. And finally, I do have y2 in terms of y1 and x1. And so y2 will be 3 copies of y1, which I'll just multiply across as 6/7 x1 minus 3/7 x2 plus 3/7 x3, finally minus x1. And if I combine the x1 terms there, instead of having 6/7 on x1, I will have negative 1/7 on x1. So there is me having solved for y1, y2, and y3, and we recover that L inverse of x1, x2, and x3 is going to be the output of y1, which is 2/7 x1 minus 1/7 x2 plus 1/7 x3, and then the output of y2, which is negative 1/7 x1 minus 3/7 x2 plus 3/7 x3, and finally the output of y3, which is negative 1/7 x1, 4/7 x2, and 3/7 x3. The astute the astute observer will notice that every term has been multiplied by this 1/7, and that is going to come into play, but it'll take us a week or so to see where that 1/7 comes from. But it is a very useful quantity that will show up in these inverses all the time. Anyway, that is our inverse linear map in this particular case. And we're going to finish off today by looking at one nice example of this property that I referred to at the end of the last video. that an inverse of a forward linear map of x should leave it invariant, and the same should be true about the forward of the inverse. So the linear map we're going to be using here is 2x1 minus x2 and x1 minus 2x2. So I'm going to claim that the following is L inverse here. I'm going to claim this is 2/3 x1 minus 1/3 x2, and then 1/3 x1 minus 2/3 x2. So this is a claim. Now let's verify. And we can verify our claim by computing really either of the two above, but I'll go ahead and compute both of them. So we'll compute both of them above. And to do that, I'm going to have to evaluate L inverse of L of x1, x2. Well, I know what L of x1, x2 is. It's given to me up above there. So I'm really evaluating L inverse of 2x1 minus x2, x1 minus 2x2. Now when I evaluate this L inverse, I'm thinking about that as the first entry. So that's going to take the role of x1 here, and the second one as the second entry. So that's going to take the role of x2. If I actually perform that evaluation, what I get is 2/3 times the first input, which was 2x1 minus x2. Then I have minus 1/3 times the second input, which was x1 minus 2x2. The second row, I end up with 1/3 times the first input, which is 2x1 minus x2, minus 2/3 times the the second input, which was x1 minus 2x2. At this point, it's to my benefit if I distribute and then later combine all like terms. So when I distribute, I end up with 4/3 x1 minus 2/3 x2 minus 1/3 x1 plus 2/3, because of two negative signs, x2. The second row, I have 2/3 x1 minus 1/3 x2 minus 2/3 x1 plus 4/3 x2. If I combine all the like terms, what I end up having is negative 2/3 x2 and positive 2/3 x2, as well as 4 minus 1 over 3, also known as 3/3 x1, or just x1. Similarly, in the second component, I have 2/3 x1 minus 2/3 x1, and I have a negative 1/3 x2 plus 4/3 x2, also known as a single copy of x2. And so we do see that L inverse and L perfectly cancel each other if I evaluate one inside of the other, and I can try this again in the other direction. So in the other direction, if I write L of L inverse of x1, x2, I can go ahead and compute L inverse right away as what's happening in the top there, and that gives me L acting on 2/3 x1 minus 1/3 x2, 1/3 x1 minus 2/3 x2. At this point, I know that the first entry is behaving as x1 inside of L, so every x1 is going to be the first entry, and the second entry is behaving as x2 inside of L. So I replace every entry x2 the second row. So that's going to give me 2 times 2/3 x1 minus 1/3 x2 minus one copy of the second row, which is 1/3 x1 minus 2/3 x2. The second row of my output is going to be one copy of the first input, which is 2/3 x1 minus 1/3 x2, and I'm going to subtract two copies of the second input, 1/3 x1 minus 2/3 x2. As before, it's going to be to my advantage to distribute and then combine like terms. Once I distribute, I have 4/3 x1 minus 2/3 x2 minus 1/3 x1 plus 2/3 x2. Into my second row, I have 2/3 x1 minus 1/3 x2 minus 2/3 x1 plus 4/3 x2. Combining like terms, it looks like I have negative 2/3 x2, positive 2/3 x2, as well as 4/3 minus 1/3 x1. I end up exactly with one copy of x1. Same business in the second row, 2/3 x1 minus 2/3 x1, negative 1/3 x2 plus 4/3 x2. I have exactly one copy of x2. So now you can see kind of how these inverses exist, and keep in mind, this goes all the way back to our very first video, this notion of L inverse L or L inverse are function compositions of these maps. And so this is why function composition can certainly be important. Anyway, I hope this was enlightening. I'll see you in the next video. Bye.